Hello, welcome back to the Unreal Engine 5 Computer Shader Destruction System series. This time we'll be adding the animation and the depth check. We will learn how to use the atomic functions, and we will do a little bit of float Mantissa hacks. I know that sounds complicated, but I hope everything will become clear. We will start with calculating nearest hit point. For that, we're gonna use atomic functions and a little bit of bitwise operations. Firstly, we have to modify our raise field intersection function. So it will return the actual hit distance instead of the gain time. If no intersection is found, we will return the negative number. It's gonna be useful later. I'm also making the get intersection distance that will return the word position hit distance for the chunks. We may find a minimum distance for each pixel, but here's a problem. We need to get the minimum distance from all the results. Luckily, there's a way to do it. Computer shaders have something called atomic functions. This is a special thing made for the computer shaders that makes syncing with computer shaders easier. For general use, the most three useful functions are these three. In our case, we're gonna use the interlocked max. It will allow us to find the maximum hit distance from all the hit points. But there's one problem. They work only for uint and int values. And our result is in float. So we'll have to do a little bit fancy bit hacking. DirectX uses a standard of a float called IEEE 7.4. Let's take a closer look how we can approach this. The general idea is that we only grab the Mantissa bits and convert to int, and we ignore the exponent bits. The way to do it is to make the exponent with a value of 1, and if we're gonna add the Mantissa bits, we're gonna go from the range of 1 to very close to the value of 2. This way we can convert the normalized float to int and back with a lot of precision. Let's implement this. Firstly, conversion from the normalized float to the uint. I'm adding 1 to the value and clamping it to this float coded in hex, which represents the max valid value. Then I'm converting it to the uint, so I can do a little bit of bitwise operations. For example, clamping only Mantissa bits. So now we have a uint value that represents the value stored in the Mantissa. We also need a function in the opposite way. Grabbing the Mantissa bits, multiplying it by the Mantissa mask just in case. Then we're adding the bits of the exponent, so we have the exponent of 1. And then converting it back to the normalized value. We need a read-write buffer that's gonna store the closest hit. The read-only buffer with the same value is needed as well. It's time to modify our main kernel. Firstly, let's change the name. Let's change it to PivotPainterDestroy find closest hit. We also have to change the name of the defines. I am renaming the num threads for X, Y, and Z. It is because they have to be unique for each kernel. I also decide the better texture to check the canvas size is timestamp. In the computer shaders, it's a good practice to skip the rest of the code when possible. So we will grab the previous time earlier. The raise field intersection function already returns the normalized distance, so we don't have to normalize it. Let's also check the hit distance if it's in valid range. And if it's not, we can use return. Notice that I'm inverting the normalized distance of the hit. It is because we don't have to initialize our max buffer, since it will go with 0 at the start. Now we can do the max operation with our result. I'm also adding the value of 1 because it will tell us later if any hit was registered. We will also make a new kernel that will handle all the logic of animating chunks. We're also doing the same trick with unique num threads. Now we will check the closest hit buffer. If the result is 0, it means no hit was found. Furthermore, we are copying checking the bounds logic from the previous kernel. We are doing the same thing with sample codes and previous time. Now getting the distance back from the uint buffer. Notice we are subtracting 1 because we added the one before, and inverting the normalized value because we inverted it earlier. With all this information, we can calculate the world space hit point. It is by getting the ray origin and multiplying the normalized distance by the ray vector. And then, like previous, we are decoding the world position of the chunks. And with that information, we'll check if the distance from the world position of a chunk to the hit point is less than 50, and if it is, we will send the game time just like before. The async compute shader has one limitation. It doesn't reset the buffer automatically. The easiest way to deal with this is to make the kernel that will reset all the buffers. Since the closest hit buffer only has one element, we only reset it at 0 index. Time to modify the code of the compute shader controller. So let's rename the class that handles our parameter declaration. I'm renaming it to fPivotPainter find closest hit. For clarity, let's also rename the permutation domain. We also have to copy the new name of num threads. The new kernel has to be updated in the implement global shader macro. Now we have to do a new class for PivotPainterAnimate chunks. So I'm copying and renaming the class of find closest hit. Don't forget to rename the defines. Also add the new macro of implement global shader for the new kernel. I am doing the same thing with copying and renaming the class for PivotDestroy reset buffers. Notice that reset buffer doesn't have the num threads defines. It is because the num threads are hard-coded. Don't forget to declare the reset buffers in the macro. Time to update and bind the shader parameters. Since find closest hit doesn't write to timestamp, it doesn't need it, so let's delete it. Instead, we're gonna add read-write uint buffer with closest hit. The same buffer has to be binded to the animate chunks with read only. We also have to bind the random read buffer to reset buffers. Now, since we got 3 compute shaders, we have to do some renaming and cleaning in this patchRenderThread method. I'm also adding the declaration of the new kernels and permutations vectors. Let's also check if all 3 compute shaders are valid. We need to start declaring the new buffers. Let's start with closest hit with random write and read-only variant. Notice that buffer is uint and has only one element. It is important to get the right format for UIV buffer. We also need the reference to the new created buffers. I'm creating the read-only buffer with null pointer because we don't need any start data. We will try to mimic the compute shader layout, so the declaration of variables and execution will be same in the compute shader controller. It means that pass reset buffer parameters are first. Let's bind the new buffer to the reset buffer's pass parameters, and let's dispatch it with group size 111. we will rename the old pass parameters to match their new kernel name. Let's remove old bind of read-write timestamp texture and bind a new closest hit UIV buffer. After the find closest hit is dispatched, we have to copy the UIV buffer to read-only buffer. Now let's create a new chunk pass parameters and bind the new parameters. It has to be dispatched with the same group as find closest hit. Now let's test it how it works. So I got an error that I forgot the declaration of hit distance. Let's fix it now. This is why it's good to have the shader development mode on. The project compiled, we can test the new behavior. So it should work now like this. Chunks appear in the radius, and we have the correct depth test. But there's a small modifications I want to make. I want to have control of disappearing distance and the delay the chunks from the hit disappear. For that I will need the inverse spread distance, which is 1 divided by the spread distance. Let's also add the max delay for the chunks to disappear from the hit point. From the PivotPainterDestroy animate chunks, let's grab the calculated distance and use it to declare the scale distance. To know if hit is valid, we only have to check if it is less than 1. So the new timestamp will be gain time plus max delay multiplied by scale distance. Let's update all the new parameters in all our structs and methods. Here I'm calculating the inverse spread distance. We also have to add these new variables to the shader structs. Do not forget to bind them to pass parameters. Since the texture and buffers are not flashed automatically in the ASIC compute shader, it's also a good idea to copy timestamp target texture to temp timestamp texture. It will prevent some artifacts in the gameplay. Let's go back to the project to make some changes to the blueprints. In the PivotPainterDestroy blueprint, I added a spread distance and max delay to the ray hit event. In the weapon component, these new parameters are copied from weapon component blueprint. So now, as you see, the chunks disappear with some delay. We have a basic functionality, but we want the chunks to be animated. The way to do it is calculate the explode vector, and with some randomization and rotation, we can move some procedural animation on the material level. But firstly, we need to calculate this new texture with the compute shader. So let's create a function that will hold of our animating of the chunks. For now, we will just use the code for animate chunks kernel. Don't forget to call the function in the kernel. We will need a new read-write texture for storing the explode vectors. I'm calling it ervo, normal and random. It will store the explode vector and pseudo-random value. The calculated explode vectors should be only valid if the scaled distance is less than 1. What I'm doing here is calculating the normalized ray direction, a little offsetted hit point, vector from every chunk to the hit point, and vector back to the player. We'll also need normalized vector to the hit point. Now, with dot product, I can calculate the lerped vector depending on the chunk position and direction of the ray. Calculated normal is also rewapped to the range of 0 to 1. We will also calculate the random float from range 0 to 1. It will be useful in the material later. As a base, we will use the word position of the chunks and some seed value. The new variables will be outputted in the new read-write texture. We also have to bind the new texture to all the methods and blueprints. Now, time for the seed. Notice I'm calculating the seed just at the passing dispatch parameters. Let's add the normal random texture and seed parameter to the animate shader parameter struct of animate chunks. We will also have to make a new texture with normal and random. It will be very similar to the timestamp target texture. Now let's bind the new texture to the animate chunk pass parameters. Don't forget the copy texture pass for the temp texture. I also forget to pass the seed parameter, so let's do that now. Back in the project, I want to make few modifications. In initialize textures, I created a new texture, normal random. It is pretty similar to the timestamp texture, except it uses the different format. Here I am using 16-bit RGBA, but you can experiment with 8-bit if you want. I'm assigning it to 16-bit data to get a proper filter method. As previous, I'm assigning this texture to each dynamic material instance with a parameter name normal random. I'm also assigning origin extend texture because we're gonna need this in the material. Back in the event graph, I'm binding this new texture to the compute shader blueprint. Moving forward, I created a new material function for animating the chunks, so it can be easily adapted for every material. Let's take a closer look how it works. Here I'm grabbing the Pivot Painter UVs and using it as Pivot Painter UVs reroute node. Like previous, we are calculating the distance from the timestamp texture, clamping it to the positive values, and dividing it by the exposed effect duration. Calculated normalized time will be used as base for the animation. I'm also grabbing the origin extend texture, and with using the global material function pivot painter to decode position, I'm calculating pivot word position. In the difference section, I'm packing the normal from the normal random texture. The calculated vectors will be used as explode normal. Here I'm grabbing the calculated in the compute shader random value and also using it to calculate a new pseudo-random value. We're gonna use it in the random rotation. Here I'm calculating the movement vector. It is basically using the normalized time and it lerps explode normal with the gravity vector. The output value is normalized. This section is responsible for the pivot's offset. What I'm doing here, I'm using the explode strength material parameter and with some randomization, I'm calculating the random velocity for each chunk. But to calculate the final word position offset, we need one more thing. We need the rotation for each chunk. The way to do it is calculate the helper vector that will fit the current explode normal with some a little branching. The helper vector is used to calculate the rotation axis. With some random randomization and input parameters, we can calculate the new randomized rotation, and with some custom HLSL expression, we can calculate the new rotation matrix. The calculated matrix will be used to rotate the vertex normal, the vertex tangent, and the vertex bitangent. The last two are very useful if you are inputting the normal map. I'm also doing a little bit of branching because I want to skip all the unnecessary instructions when chunk is not activated. I also added the static switch that adds supports for the normal map. Just remember to disable the tangent normal in the material properties. The created rotation matrix has also one more use. We can use it to rotate the vertices of the chunks. But firstly, we have to center each chunk. With the chunks in the center, we can rotate each chunk using the rotation matrix. After the chunks are rotated, we need to add the pivot position again. For the optimization, I also created one more thing, vector to the pivot. I'm using it to match the vertex when chunks are not visible. It will make rendering them a little bit faster. So as you see, I'm comparing the normalized time to value very close to 1, and if it's greater than this value, I'm merging the vertex, and if it's not, I am adding the pivot offset to the rotation of the chunks. Also, if chunks are not activated, the world position offset is equal to 0. The last thing is to calculate the opacity. It is very basic remapping over normalized time. And that's enough for today. Next time we will be adding the collision support and we will deal with another use case scenarios. And remember, if you get lost in any step, you can grab the whole project from the GitHub. And I hope I will see you in the part 3.